Buenos días. Buenos días. Bueno, pues muy bienvenidos. Es un gran gusto estar con ustedes comenzando este congreso en celebración de los 75 años del Instituto de Matemáticas de la UNAM. Es realmente un gran honor. Y es un honor empezar con la conferencia del profesor Jack Milnor, quien nos acompañó aquí en 1956 en un congreso que fue un parteaguas en la topología mundial y en la topología mexicana. Qué bueno que nos acompañen, es un gran gusto, y le cedo la palabra al doctor Alejandro Adem.
Muchas gracias. Para mí es un placer introducir al primer ponente de esta conferencia. Yo fui estudiante aquí en la Facultad de Ciencias, recuerdo muchas sesiones aquí en este auditorio, y en particular haber leído con mucho cuidado los trabajos del profesor Milnor, en particular su libro Clases Características con James Tashev, que es un libro clásico, y ahora tenemos una versión en español que se va a presentar durante esta conferencia y a la salida del auditorio. Entonces los conmino a que compren una copia porque es un libro increíble y a lo mejor el autor lo puede firmar, ¿no? ¿Quién sabe? It's a pleasure for me to introduce the first speaker of this conference. As I said, my introduction is going to be short because if ever there were a mathematician that does not require an introduction, it is John Milnor. Suffice it to say that he did foundational and amazing work in algebraic and differential topology and in dynamical systems that opened the path to most of us here working in those areas to this day. He is one of the very few mathematicians that have won the Wolf Prize, the Fields Medal, and the Abel Prize. So let me now introduce John Milnor from Stonybrook University. Thank you. I should turn this on.
Testing. Is that working? Yes. I think it would be easier if I stayed here. Sure. But could you hand me the... thank you. Well, I'm very happy to be here in Mexico once more. UNAM has changed a great deal since I first visited here 61 years ago. It was a marvelous conference then, but I hope that this will also be a marvelous conference. So let me just figure out what I'm doing. So first of all, just a brief outline of what I want to talk about. General problem is to understand the actions of a smooth group on a smooth manifold, and to study the quotient space. And I'll want to study two examples in particular. One is the group of Moebius transformations of the Riemann sphere. It's the group of all holomorphic maps from the Riemann sphere to itself, and that will act on the space of effective divisors on the Riemann sphere. So I'll explain more precisely soon, but this is just a brief description of what the talk will be about, understanding the quotient space under this action. And the second, a much harder example, will be studying curves in the complex projective plane. And here, the automorphisms of the projective plane act on the space of curves, and we want to study the quotient space. So in both cases, some parts of the quotient spaces are beautiful objects to study, but other parts are rather nasty. And the basic problem I want to study is how can we understand which parts are which parts are good to study, and which parts are would be very awkward to work with. We'll just first start a kind of toy example to illustrate the kind of problem that I want to talk about. So I look at the additive group of real numbers acting on the real plane by multiplying the first factor x by e to the t, and the second component y by e to the minus t. So most orbits under this action are smooth curves. But there's just one exceptional orbit, the origin, which is a fixed point of the action, and that is a bad point which will mess up the quotient topology. Because in the quotient topology, we want to look at the space of orbits of this map. So each of these curves that you see on the screen will be identified to a point. And notice that, for example, that the positive x-axis is one point, will represent one point in the quotient space. And the origin would represent another point in the quotient space. But this is very awkward since the closure of the positive real axis contains the origin. So in the quotient space, we'd have an awkward situation in which the closure of one point contains another point. Well, here there's a simple remedy for getting rid of that problem. Just throw away the origin. So look at the punctured plane, and we can look at the quotient space under this action where each of these curves gets identified to a point. And this will be a nice smooth manifold locally. So if we take any point, let's see. Well, this is very hard to see, I guess, but if we take a point, say, on the x-axis or any point anywhere here, and take a little transverse line, then each of the orbits through that line intersects it exactly once. So the quotient space there just looks like an interval on the real line. And this is true all around, so you might think that we're just getting a circle as the quotient space, but things are not so nice. Because if you look at a little transverse on the positive real axis and the corresponding on the positive y-axis, you'll find that every point on one belongs to the same orbit as a point on the other. That is, every point except off the axis itself. So this quotient is an example of a space which is not Hausdorff. We have two distinct points, but every neighborhood of one intersects every neighborhood of the other. So this is the kind of thing that we may have to worry about. We may have a quotient space which is locally Hausdorff, but not actually Hausdorff. But this is often enough to work with because locally you can understand everything. And if you'll excuse me, I'm going to sit and tie my shoelaces before I trip. Okay. So, first part, studying the space of divisors on the Riemann sphere. So, by definition, a divisor is just a formal sum, or it's an element of the free additive group with one generator for each point on the Riemann sphere. So, it's just a formal sum of points, each counted with some non-negative multiplicity. Well, the space of all such divisors has a very simple structure. It's just a complex projective n-dimensional space. Because for any such divisor, you can think of it as a set of zeros of some homogeneous polynomial with n+1 complex coefficients. But notice that if we multiply the polynomial by a constant, the set of zeros won't change. So the space we're looking at is just the quotient space. Non-zero points in an n-dimensional vector space over the complex numbers where we identify points if they belong to the same line through the origin. So this is a nice compact space. We have a beautiful Lie group acting, a group of Moebius transformations, but the quotient space is not so easy to study. Well, first, now we have a n-dimensional space here of divisors here. When I talk about dimension, I'll always mean dimension over the complex numbers. So we have an n-dimensional space, and acting on it, we have the group of Moebius transformations, which is a three-dimensional space. So in general, we'd expect to find a quotient space which is n minus 3-dimensional. But, well, that's a good first approximation. Well, how do we distinguish? So the quotient space is a big space. How can we distinguish two different points in it? Well, we'll try to give a complete description, but there are two very simple invariants which will be important in the discussion. One is just the number of points. Here I define the support of a divisor just to be the corresponding finite subset of the Riemann sphere, where we forget all about the multiplicities. Then the number of points in the support is one basic invariant. So, for example, if that's equal to the degree n, that would mean the points are all distinct. This is the most non-degenerate case. And the opposite case, if all of the points are crowded together into one point, then this would be k equals 1. Another basic invariant is the largest multiplicity which occurs. So here in the most non-degenerate case, where the points are all different, this maximum multiplicity would be 1. And in the opposite, most degenerate case, where all the points come together, it would be n. So these are rather two integer invariants, both between 1 and n, but they're rather different, and one increases usually while the other decreases. Now, one very important concept that we'll be using over and over is the stabilizer of a point in the space under this action. So that's just the subgroup of G consisting of all group elements which map the point, that is the divisor, to itself. And the first basic question we have to understand is, when is this stabilizer finite? And there's a very simple answer here. The stabilizer is finite if and only if the support has at least 3 elements. And I could say something more here. It's either finite or else it's a Lie group, uncountably infinite. You can't have a infinite discrete group. So there's just two possibilities. It's a finite group or a non-trivial Lie group. Well, this is easy to prove. If the group acts mapping the divisor to itself, then it also must act on the underlying subset, the support. And so it will give some, and remember these are group elements, they're diffeomorphisms, so that they must be one-to-one, so that they must give a permutation of this finite set. So we have a natural map from the stabilizer to a finite group. Now suppose there are at least 3 points in the support. Well, the basic property of the Moebius transformation is that, or the group of Moebius transformations, is that it takes any 3 points to any other 3 points. So it's simply transitive on the set of 3 tuples of distinct points in the Riemann sphere. So if we have a permutation which fixes all of each point in the support, it will fix at least 3 points and must be the identity, which means that the group G sub D, the stabilizer, is a finite group, isomorphic to a finite group of permutations. Well, the other possibility is that we have at most 2 points in the support. So, as I said, you can take a Moebius transformation taking any 3 points to any other, so we can take any 2 points to 0 and infinity. And then we have a simple Moebius transformation, multiplication by a constant, where k can be any non-zero complex number. So in this case, the stabilizer is at least the group of all multiplicative group of all non-zero complex numbers. an example of a complex Lie group. If there's a point interchanging 0 and infinity, then there'll be one other element in the more elements in the stabilizer, but it's always a Lie group. So I'll concentrate on this space of divisors with finite stabilizer. It's an open subset of the full group of full projective space. And the definition we'll call the moduli space for divisors under the action of the group of Moebius transformations. Well, the first statement is that this is a T1 space. By definition, this means it's a space in which every point is a closed set. Or in other words, it means that the action on the space of divisors, every space of divisors with a finite stabilizer, every orbit is a closed subset. Or another way of saying this, if you take any limit point if instead of working in D-stab, in the things with finite stabilizer we work in the full group of divisors, then any limit point must have infinite stabilizer. This outside the space we're looking at. Well, to prove this, we have to look at elements which are close to infinity in the group G. Here, G is a non-compact group, and whenever you have a non-compact group, you can put a kind of topology on it, adding a point at infinity and saying that things that are outside a large compact set are close to infinity. So we have to understand what it means for a Moebius transformation to be close to infinity, or in other words, outside of a very large compact set. Well, P1, we think of it as the Riemann sphere. It has an actual spherical metric. I look at the open epsilon neighborhood of any point. And the lemma states this. Given any epsilon, there's a large compact set with the following property. Any G, which is close to infinity, in other words, outside this compact set, we can find 2 points P and Q such that G maps the epsilon neighborhood of P to something which covers everything except the epsilon neighborhood of Q. So this is a kind of picture. I've drawn, the two boxes are supposed to represent two different copies of the projective of the Riemann sphere. The reason for that is that P may be equal to Q or may be distinct, so the pictures would look very different in those cases. But if we just think of this is mapping one copy of the Riemann sphere to another, it looks clearer. So the statement is that, well, let me just explain the picture here. So everything inside the red disk, inside the red loop, maps outside of the dotted red loop too. So a point here that's inside maps to a point here that's outside. Everything that's outside the red loop maps inside the red dotted loop and therefore maps inside the neighborhood of Q. Well, I won't try to prove this in detail, but here's just a few words to say how one would prove it. First of all, look at the group of diagonal transformations. So if we just think of, if we identify the Riemann sphere with the complex numbers together with a point at infinity, that just amounts to setting y equal to 1 and looking at multiplying the x coordinate by a constant. Here x and y are complex variables. So the proof in that case is easy. Just stretching out, you can map a little disk so it covers everything except a big disk. And it's just elementary linear algebra to show that any Moebius transformation can be written as a product of a rigid rotation of the Riemann sphere, followed by such a diagonal stretching, followed by another rotation. So now I want to prove this theorem that if we have at least 3 distinct points, then every orbit is closed as a subset of the maps with finite stabilizer. So we choose epsilon small enough so that any 2 points of the support have distance at least 2 epsilon. Or that means that if we take any ball of radius epsilon, it can only intersect one of these neighborhoods. And now using this epsilon, we apply the distortion limit and find 2 points P and Q. So we get a picture like this. So there's at most 1 point of our divisor inside the neighborhood of P. All the others, that's the basic property that each epsilon ball contains at most 1 point. So everything outside of the red set will get mapped into the blue set. And that means that all but one of the points will be crowded into an epsilon neighborhood. And now, suppose that we, given a sequence of points, so we're taking different images of the given divisor under different group elements, and suppose that so we're working within a given orbit, suppose that we're converging to a point D prime. Just 2 cases. If the GI all belong to a compact subset, if the GJ all belong to a compact subset, then the limit will still be in the same G orbit, because we can choose a convergent subsequence. But if the GI are tending to infinity, then we can apply the distortion lemma with epsilon going to 0, and that means that all but one of the points will be squashed into a smaller and smaller disk. So in the limit, there'll only be 2 points. 1 point corresponding to the red disk, and everything else will be squashed inside the blue disk, which is squeezing to a point. So that will prove that we've gone out of the space set of points with set of divisors with 3 distinct points and gotten into the bad set. Well, I want to look, what does this quotient space look like? It seems like a very elementary problem, which should be obvious. We just have a finite number of points on the sphere. Counting multiplicities, we're allowed a very restricted group of transformations. And what does the quotient space look like? Well, we'll first look at we can't look at the case where n is less than 3 because we would need to have 3 distinct points. So the first possibly interesting case is n equals 3, but any 3 points look like any other 3 points after applying a Moebius transformation. So M3 is just a single point, which is certainly a well-behaved space. Now M4, 4 distinct points, here we get a copy of the Riemann sphere itself. And let's give an outline of the proof, assuming you know some classical differential geometry. 4 distinct points in P1 determine a 2-fold branch covering space. We take first remove the 4 points, then take a 2-fold covering space, and then fill in the points. We'll get a smooth torus. And classically, this is classified by one single complex number called the J invariant. So the open subset corresponding to the divisors with 4 distinct points is isomorphic to the complex numbers. But there's only one other orbit to consider, an orbit with only 3 distinct points, and that will always be in this G orbit, where here the double parentheses means the G orbit through the given divisor. So we have a divisor with P counted twice, Q and R, and there's only one of these after acting on the Moebius transformations. So we have a copy of C plus one extra point, and it's not hard to check that this just corresponds to the one-point compactification, which is a sphere again. So the first two cases look very easy, but from here on, it gets much worse. So theorem for n5 or more, the quotient space is never Hausdorff. But what we can say is that there's a maximal open subset, which is Hausdorff. Now this is not something that's true in any space. For example, the toy example we considered, we had a maximal open subset which is locally Hausdorff, but it wasn't Hausdorff. But in this case, there is a maximal open subset which is actually a Hausdorff space, and it has a simple description. It's the set of all points of n with maximum multiplicity less than n over 2, where n is the degree. So it's, I'm tempted to think of political or economic examples. If you have too much power concentrated in one point, then things get very awkward. So if half of the multiplicity is concentrated in one point, or more than half, then we're in a bad situation. But as long as it's less than half, then it's okay. And now this is something which was completely unexpected to us. This quotient space is compact for even values of n, but it's non-compact for odd values of n. It turns out to be true, but so in general, we also have the following. Whether it's compact or not, it's always an orbifold of complex dimension n minus 3. This is the expected dimension, but an orbifold means that it locally looks like the quotient of a compact n minus 3 dimensional vector space by a finite group of automorphisms. So there are definitely singular points. These correspond exactly to the curves which have exactly to the divisors which have extra automorphisms. So for example, if you have a set of points, a random set of points in the sphere, there'll be no way of getting an automorphism which moves them. But if, say, you take the vertices of an icosahedron, this is a set of 12 points in the sphere, which has a very interesting group of automorphisms, and this will correspond to an orbifold point in D12. Or D stab 12, or M step 12, I mean. And this is the best you can do. Whenever you get outside of this compact set and you have one point with at least half of the multiplicity, half of the total multiplicity, then the space is not even locally Hausdorff. Well, I won't try to prove this in detail, but just say a few words to indicate how it's proved. So first of all, there's a basic definition that an action of a Lie group on a manifold is proper if it has the following property. Given two distinct open sets, or it's usually, so given 2 points, I should say, x and y and x, there are neighborhoods u and v, a neighborhood of x and a neighborhood of v, which are small enough so that the set of group elements which map some point of u to some point of v has compact closure within the group. So you can't have a situation where you can have, as you get take the neighborhoods to be smaller and smaller, you have to go further and further out towards infinity in the group G. If that can't happen, an action is called proper, and the standard theorem is that the quotient of a Hausdorff space under a proper action is again a Hausdorff space. This is a fairly elementary argument once you've understood the definitions. And using the distortion theorem, one can show that the action on the space of divisors is proper whenever this maximum multiplicity is less than n over 2. And this is proof which is very similar to the previous proof I gave you using the distortion theorem. I'll later use a similar theorem for curves, so I won't give further details. But now, the claim is also that the space is not locally Hausdorff when we get outside this set and when we have degree at least 5. So just to simplify things, I'll just consider the first case where n is 5, and I'll consider the following two divisors. D is any divisor of degree 2, say 2 points in the finite plane, together with a point at infinity counted 3 times, and D prime is a divisor of degree 3, 3 points in the finite plane, plus the point at infinity counted 2 times. And now I look at this simple transformation. I take some, say, large real parameter and multiply by k squared, by kappa squared, and divide by z. So we get an inversion which takes all points inside the huge sphere of the huge ball of radius kappa and multiplies it outside this sphere. So points in a large part of the complex plane get mapped very close to infinity. Now we just modify the definition slightly. We take D2 plus G kappa of D3 and D3 plus G kappa of D2, and I claim these belong to the same G orbit, because if we just apply G sub kappa to the left side, since G kappa is an involution, it maps to here. And if we multiply this by G kappa, apply G kappa to this, we get D3, and apply G kappa to this, we get this. So these two things belong to the same orbit. Now we let kappa tend to infinity. Here, the first one, this is getting closer and closer to infinity, so we're converging to this. And this is getting closer and closer to infinity, so we're converging to this. So we see that the image points pi of the image of D in M5 and the image of D prime in N5 have the property that every neighborhood of one intersects every neighborhood of the other. So this proves that the space is not Hausdorff. And but here D prime can be arbitrarily close to D because, because if we here we can choose any 3 points in the complex plane. So we can choose one of them very close to infinity, and then we'll get very close to this one. So this proves that the space is not even locally Hausdorff at that point. And the other cases of this, the proofs are very similar. Okay, now I'll go on to a different, much harder subject. And I suspect that if there are probably algebraic geometers in the audience who will know much more about this subject than we do, but we'll be happy to stand corrected if we are repeating things which are well known. But in any case, we just need some definitions. An effective one cycle, the point is if we just look at the space of complex curves, it's a little awkward since it's non-compact. For example, if you have a curve consisting of two distinct lines, then we can move them together and get a curve consisting of a single line counted twice. So to find it seems more natural to work with a compact space by allowing multiplicities to the curves, just as we allowed multiplicities to the points in studying divisors. But this is just, you can think of it as just a kind of compactification of the space of complex curves. And again, the same kind of argument shows that this is a structure of a complex projective space, although of a much larger dimension. So we just take a look at the set of all non-zero homogeneous polynomials of degree n. The zero locus of this will consist of a collection of irreducible curves, each counted with some multiplicity. This is just a statement of unique factorization for polynomials and homogeneous polynomials in three variables. So this gives us a space of one cycles, and then we look at the group of all automorphisms of the complex projective plane. This acts on P2, and hence acts on this space of compactified space of curves. And again, the stabilizer will play a fundamental role. It's just the group consisting of all projective automorphisms which map the curve to itself. And again, the stabilizer may be either finite or infinite. If it's infinite, it will always be a Lie group. So the two cases are basically different. If we pass to the quotient space, if we have a finite group, then the quotient space will look very much like G itself. Or, I'm sorry, the orbit will look very much like G itself. It's just coset space of G modulo a finite group. But if the stabilizer is infinite, then the orbit space will be lower dimensional. Just as in the toy example, we had one special point which was a lower dimensional orbit. In this case, any orbit which is lower dimensional will cause trouble, and we want to avoid it. So first of all, what is the space of curves with infinite stabilizer? They were first studied in the 19th century by Klein and Lee, who called them W curves. And there are many, it's easy to give examples. Here, I should warn you, I'm drawing pictures in the real plane, of course, but you should think of these as being just the real traces of complex curves. So the simplest example is just a group of concentric circles. Clearly, you can rotate them all simultaneously. You've got an infinite group of transformations. The real picture is a little deceptive because it makes them look disjoint. But actually, if you have any two degree curves in the complex projective plane, they have to have four intersections counted with multiplicity, so that in the complex plane, these things are not disjoint, but you can still rotate. Here's the simple cusp curves. I don't know whether it's x squared equals y cubed or the other way around, but if you multiply one coordinate by t squared and the other by t cubed, it will map to itself. This is a little less obvious. We have any number of points through a common point, but one other line which is outside of doesn't pass through this common point. Then we can make a Moebius transformation taking this exceptional line to the line at infinity, and then we just get a picture consisting of the origin and a number of points through the origin. And then we can take a uniform expansion, multiplying by a real constant, and get an infinite group of transformations taking this to itself. Of course, I'm describing it over the reals, but over the complex numbers, we get an infinite dimension. We get a complex Lie group with dimension at least 1. Well, I want to look at the algebraic set consisting of all cycles with infinite stabilizer. So this is any algebraic set in a complex projective space is a union of maximal irreducible subvarieties. And in this case, they're not all the same dimension, so different irreducible subvarieties have different dimensions, but this is all very well understood. You can completely classify these things and understand exactly what they are. It's a somewhat detailed list, but not at all difficult. So, and again, we have this property that the stabilizer is finite if and if the orbit has full dimension 8, where 8 is the dimension of the group of projective transformations of P2. So we have this fact. So whenever we have infinite stabilizer, then this will have dimension less than 8. And for finite stabilizer, it will have dimension 8. So now we can form the moduli space. This, again, we restrict to the open set consisting of cycles with finite stabilizer, and form the quotient space, which we'll call the moduli space for plane cycles of degree n. And, well, there are no curves with finite stabilizer of degree 1 or 2, a line or a quadratic curve always has lots of automorphisms. But it gets more interesting for M3. Here, the moduli space is canonically isomorphic to something we've studied already. In fact, I describe M4 in terms of its relation to cubic curves. So we have, in fact, we get a precise isomorphism. This is not just a topological isomorphism. It preserves complex structure. It preserves the orbifold structure. So each of these spaces has 2 points with extra symmetry with a larger stabilizer. I guess it's easy to describe for divisors of degree 4. You can have a divisor of degree 4 consisting of 4 points on a square, and then we have the full group of automorphisms of the square mapping this to itself. Or we can have the vertices of a tetrahedron, and then we have the full tetrahedral group with 12 elements acting on it. These correspond to the elliptic curves with extra symmetries. Now, in each one, there's also one point which I'll call improper, in that the action is not locally proper there. In the case of a curve, it's a curve with a double point. And in the case of a divisor, it's a case of a divisor of degree 4 where the 2 points come together. And these correspond precisely to each other. If we take divisors of degree 4 and move it to the points together, the corresponding cubic curves will tend towards such a singular curve. Well, that's all for the things that we really understand, but it is a theorem that this quotient space we've defined is a T1 space. Points are closed sets. This is a kind of cartoon showing here the screen is supposed to represent the set Cn of all curves of degree n, circles, one cycle is a degree n. We have this Wn, which is a algebraic subvariety made of many different pieces, but it's compact and well understood. If we take any curve here, we can form its G orbit. This red line is supposed to indicate the G orbit. And the assertion is that the closure of this orbit just consists of the orbit itself plus points in W sub n. So the boundary of the orbit is contained in W sub n. This is a theorem which I think was proved by Gazzetti in 1936 for curves, and Alofi and Faber extended the proof to cycles. And it's not, I don't know a sort of a direct proof of this. Their discussion depends just on studying many, many special cases. But again, it's any case is a known theorem. So every point of Mn is a closed set, which is not much, but it's some restriction on how bad things can be. Now, just as in the Moebius transformation, we need to use the distortion lemma for things which are going out towards infinity. So it's very similar. Given epsilon, there's a compact subset of this group of automorphisms of P2, which has the following property. For any G which is outside of this compact set, there are two cases. There may be a point and a line such that the G of the neighborhood of the point together with the neighborhood of the line covers the whole space, so that everything outside the blue disk maps into the blue region around L. Or there may be the opposite situation, so that G maps the image of the neighborhood of L together with the neighborhood of Q covers the entire space. And notice that these two cases are not really different. We can just, if G satisfies one, then G inverse will satisfy the other. So if we have a group element G, we also have a group element G inverse. So there's not much difference. And the proof is very similar to the proof in the Moebius case, just a few more details. Okay, now the next part is a lot of fun for me because it goes back to work I did about 50 years ago. So we start with the singular point of a complex curve and let n epsilon be a small round ball around it. And then we approximate the curve. C is a singular curve. We just take any curve which is very close to it. Generically, it will be smooth. And then we take the intersection. So this is a kind of a schematic picture. We have a singular point of the curve C. We take a round ball, and which then if we take a smooth approximation to the curve and intersect it with the ball, we get a compact Riemann surface with boundary. This is a one-dimensional picture, but so these boundary points here should represent a curve, a simple closed curve. And, oops, pressing the wrong button again. And this boundary circle really should be a three-sphere. So in this case, for example, if this curve is a simple cusp, then the curve would be a trefoil knot, and we get a beautiful picture in which SP would be a surface of genus 1, whose boundary is the trefoil knot. Well, so I'll call the genus of this curve SP the genus of the singularity, and this is an object which is pretty well known. For example, we take a cusp singularity in this quite general form, x to the e equals y to the q, where p and q are relatively prime. Then there's just this simple formula. So for example, for this 2-3 cusp, we get 1 times 2 over 2, which is genus 1. Or another example, suppose we take a union of smooth branches through a point. Then the genus is just the sum of the pairwise intersection numbers minus 1. So in this case, we have 3 different pairwise intersections. The two curved branches have intersection number 2, and the straight line has genus as intersection number 1 with each of them. So here the sum is 1 plus 1 plus 2, subtracting 1, we get a genus of 3. Well, I need basic property for what I want to do is a monotonicity, because I want to compare the genus invariants for genus of different curves. And the monotonicity property is that if we have one Riemann surface contained in another, then the genus is monotone. Well, the terminology, I'm not quite sure what terminology to use here. Riemann surface usually means a compact surface without boundary. I want to look at compact surfaces with boundary, and I want to consider the case where there are many components, so I'll just, if there are k different components, I'll think of it as a union of disjoint compact Riemann surfaces with boundary. And I suppose that this union is contained in another Riemann surface, then we have this monotonicity property for the genus. And I'll leave the proof as an exercise for those who are interested. And another thing we need to know is how to compare the genera of a Riemann surface with sub-Riemann surfaces. So for example, suppose we start with a closed Riemann surface S, so no boundary, and cut it up by a number of disjoint simple closed curves. And suppose that the result has L different components. Then the genus of the whole non-singular curve is the sum of the genera of these pieces plus a correction term. K is the number of boundary circles, L is the number of components of the complement, and 1 is a correction factor, essentially coming because I'm assuming that this curve is closed and these are not curved, so there's an extra term of 1 there. And well, this is you can prove this directly, or you can derive it to the corresponding formula for Euler characteristics, which is much simpler to state. Since the circle has Euler characteristic 0, it doesn't contribute anything. So if we cut something along a circle, the Euler characteristic doesn't change. We just get the sum of the Euler characteristics of the pieces. And then you can translate to get that formula. Okay, so I want to do something similar to what we did for the case of divisors, and find a hypothesis which implies proper action. So the difference is that now we have to consider not only lines but also points. So for any line in any specified curve, we can do something very similar. We form the intersection of an approximating smooth curve with a closed neighborhood of the line, and we get some possibly disconnected Riemann surface with boundary. And the lemma states the following. Suppose we look at the complement of this neighborhood S piece. So remember, we have a smooth approximation. We have a small neighborhood of the point P, and we cut away this small neighborhood and look at what's left. If the genus of this is greater than the genus of the line for every point and every line, then it follows that the action is locally proper. And with a little more work, you would find conditions for it to be proper over an open set, but let me stick to this. So this is the idea of the proof. We suppose that the action is not proper, then we can apply this distortion lemma. We'll find a point and a line so that the group element takes everything outside of the neighborhood of the point into the neighborhood of the line. Well, here we have everything outside of the neighborhood of the point, and here SL is everything inside a neighborhood of the line. So if this maps into this, then by the distortion lemma, the monoticity property, then this should be less than or equal to this. So if it's not, that proves, sorry, if it's not, that proves that the action must have been proper. Well, now what is this space complement of SP? Let me call it SP star. We know that SP union SP star is the whole smooth curve. And NP intersect SP star is just the union of K circles. So we can apply this scissors and paste equation to get a precise description. The genus of a smooth curve of degree n is classically n minus 1 choose 2, so that is well known. L is the number of components of the number of components of SP plus the number of components of SP star. In most cases, that's just 2. In exceptional cases, it could be larger, but let me forget that possibility. And it's convenient to put the other term, add the K term to the genus of P term, and define the augmented genus to be the genus of SP plus the number of boundary curves minus 1. So K is always at least 1, so this is greater than or equal to SP. This is a very convenient invariant to use because we can apply a theorem of Mumford, which about singularities of curves, and conclude that this is greater than 0 if and only if P is a singular point. So for example, if we just take a simple crossing point, that would have genus 0, but 2 boundary curves, so G would be 0, but G plus is 1. Adding in that extra term means we can detect all singularities this way. Now, just the lemma, together with the lemma on the previous slide, this formula gives us the following. Suppose the augmented genus of a point plus the genus of the line, singularities along the line, is less than n minus 1 choose 2 for every P and every L. Then the action is locally proper at C, and with a little more work, we could get a criterion for being proper throughout an open set. So let me just give a simple corollary of this. Suppose we take a curve like this, which has no singularities other than simple double points and cubic cusps. So if n is greater than or equal to 4, then the action of the group of automorphisms in P2 is locally proper throughout this open set U. In fact, with a little more work, you can prove the action is proper. So the quotient is an open subset of Mn, which is a Hausdorff space. Well, that's the end of the talk proper. Let me just quickly put on a list of references for anyone who wants to check further. That's the end.
Any questions?
So, the divisors in P1 can be seen as unordered tuple of points, right? And
yes.
So, possible repetition. So, if you do the same thing you did in the first example with ordered tuple of points.
I'm sorry?
If you do the same,
yes.
But now a quotient with PGL2, but with ordered tuple of points, you would obtain the moduli space of n-pointed.
Well, you want to talk about unions of points in P2?
No, I talk about the points in P1 when you do the quotient.
Yes.
By the PGL2 action in the divisors. If instead of using divisors, you use just ordered tuple of points. So P1 times P1 times P1, n times divided by PGL2 in the sense that you did, okay. You would obtain M0n, the moduli space of genus 0 curves, right, with n markings, right, except not the stable ones, but, And then if you so it looks like what you're doing is dividing that by the action of the symmetric group up to perhaps generic locus. So in particular, when you get the compact case, is that a quotient of M0 and bar under the Knudsen growth and decompactification model symmetric group?
So if I understand what you're saying, you want to choose an ordering of the points, and then, so this will be some sort of finite branch covering space of what I'm looking at?
Exactly. But that finite branch covering is very well known, right? It's the moduli space of genus zero curves with n points.
Yeah, well, I haven't thought about this. I better not try to answer.
Okay, thank you.
We're over there. Let's see. ¿Dónde?
For the younger ones, these spaces they seem to be very rich, a little awkward to work with, but why these actions and these spaces? Is there a motivation for the younger ones to work with these specific spaces, or do you find these examples interesting for some reason you can explain to us?
I don't have a very good answer to that. It just seems to me to be a very natural question. One is interested in curves, and if two curves are equivalent under a projective transformation, then they're essentially the same curves. So we're just studying the space of all have a curve in P2, and this is a very rich object. It seems to me we want to understand it. This is some attempt to understand a little bit of it. I should mention that the algebraic geometers have studied this long ago. Mumford's book contains a section on this thing for hypersurfaces, but the language is very different, and I'm feeling very awkward in translating what we are doing to what the geometric invariant theory says.
Well, let's thank the speaker one more time. La siguiente plática es Alfonso.